So far in this session, we have reviewed what we saw in the previous session about the general idea about algorithm complexity. We have seen an example of how to compute the trace of execution for the traversal of one list, and so that was linear. We have introduced the quadratic complexity using that not optimal algorithm to find the repetitions, to count the number of repetitions of all the elements in a list. And we have given the definition of what it means to be optimal and what the complexity, not of an algorithm, but of a problem is. And now that would be basically all for a traditional algorithms and data structures course. But here we are working with Python, which is a very, very, let's say, fast and very, very well used programming language, and it has some added bonuses built into it. So I'm going to just briefly stop into one of them, parallel programming. In some Python code, we can run some functions, some built-in subroutines or some built-in functions that are very, very, very fast. They are very, very fast for different reasons, but the main one is that they can run in parallel. They are implemented under Python in the C programming language, which is lower level, and that helps the code run faster and in particular run in parallel, run at the same time in different processors of my machine, of our machine, which results in code that runs generally faster. Okay, and let's see an example here with the sum function in Python. Let's remember the compute average traversal function, where I just computed the average of a list by traversing all its elements and adding them up and then dividing by the number of elements. And I can do the same thing using Python's built-in sum function. So this sum of a random list basically does the same that the loop used to do, adds up all the elements in a random list, and then I divide by the length of the list. So these two things are doing essentially the same thing. In terms of the algorithms are the same. The only difference is that because this is Python, this is working using fastest, more optimized C code and is likely running in parallel. Okay, so the algorithm is the same, but what happens with the computation time? Well, if I compute and plot them, they have a similar tendency, which is very nice to see. They are both linear time algorithms, but when I compare the time, the version that runs in C, the sum version, is much faster. Okay, so this adds one final dimension to my discussion about algorithm complexity, and I'm not going to focus on this course, but I think it's important to say it. We are going to be focusing on traditional conception of algorithm complexity and see their asymptotic complexity and follow the trace of execution and all of that good stuff. But when you are programming in Python, you also need to take into account that you have all these functions that might make your code actually faster in terms only of the execution time. What's the complexity class of these two algorithms? It's the same. They are both linear. Okay, this is the same situation that I had way back in the beginning of the session, where I have two lines and one has a smaller slope than the other. Okay, this is exactly what's happening now. So these two algorithms have the same asymptotic complexity. They are both linear, but because this is likely running in parallel and using, let's say, 8 processors, I'm dividing the time it takes to run the algorithm by 4 by 8 approximately. Okay, then there are other things to be taken into account, but I have a multiplicative constant that's smaller than 1, so that's making my time smaller. This thing is still linear, but the running time is a little bit smaller. Here I can see that it's linear, okay? So even though this doesn't really affect the discussion of complexity that we have been having, this is something worth remembering. What do you want to do when coding Python? Well, first you want to be coding an algorithm that's optimal for your problem. Once you have that, if you can implement it using this type of functions in Python that make your code faster, then you should definitely do that. And that is for this session. We have seen quite a lot of concepts in terms of complexity. We saw that constants don't matter. We saw linear time algorithms, constant time algorithms again. We saw the new class quadratic time algorithms, and we thought about how plotting the times can help us sometimes and sometimes not so much. And we even got some time to think about what an optimal algorithm is, how to define the complexity of a problem, and to think a little bit about the relationship between algorithm complexity and running time, and in particular with Python built-in functions. See you next time when we will be speaking about sorting algorithms.